So here's my good example. First thing you'll notice is, and this is the same end paper, right? I've got a directory structure, and there's no right way to do this. There's just some principles. This is how I do it. My process is always evolving. You may have nitpicks. You may have better ways to do it. Leave them in the comments. But as a general rule, I like to put, all right, assets. These are fixed things that I've brought in from elsewhere. These are pictures I've taken or plots I've copied from other papers that I'm going to cite, whatever. They're not things I generate, and they just sit there. Data. Okay, I've got an original data set. I've only got one this time, empty cars. Out. Well, I'll explain this in a minute. We've got data, figures, numbers, the paper, slides, tables. Okay, we'll look at that. Source, that's a pretty standard notation for developers. My source code's in here. I got 3 different R files. We've got a paper, slides, a README. Mine's pretty empty, but if I was to give this out as replication data for a real paper, here I would put instructions to follow-on researchers about how to use my code, how to replicate my work. And I've got my slides, and I've got this thing called Git Ignore, which I'll explain in a bit. Now the key I want to draw your attention to is a shell script. And if you've never used the terminal, you need to learn, right? This is part of the learning process, and we'll go into that in future videos. But it allows you to run commands from the command line instead of using a graphic user interface. And this is crucially important. Best practices for managing software is you want to do everything in code, because if you can write it out in code, you can do it exactly the same way every time. If you don't have it in code, if you're relying on someone manually pointing and clicking and walking through steps, that becomes an error-prone process that's time-consuming and not repeatable necessarily. So I'm running commands. Well, the very first command here is remove, forcefully remove and delete the out directory. Well, that's interesting. So every time I run this build script, I'm going to delete, I'm going to annihilate this entire folder and everything that it contains. Then I'm going to recreate it. I'm going to create this output table, figures, numbers, data, paper, slides. Now I'm going to run install packages, and let's take a look at that real quick. Okay, this basically says that if my system does not have Xtable or Stargazer, I will install them. That's pretty self-evident. And what this pipe thing here means is if this fails, the script will quit with an error code. So at any point, if this fails, it won't try and keep doing the next thing. It will just tell you, hey, I failed. Next step is to prepare the data set. Okay. This is the same code we had earlier. We're reading from the data folder, emptycars.csv, and then we're going to modify it. We're going to add metric units, and then we're going to write the output to out data empty cars with metric. Well, that's interesting. So we still have this other CSV folder, but now, or the CSV file, but now it's in an output directory. And my rule, the way I do this, is the output directory contains every artifact that's built by my code. And again, going back to build.sh, I annihilate that entire directory every time I run this script. So this is a little counterintuitive. You're writing a 300-page dissertation. Maybe it has dozens of tables, hundreds of figures, hundreds of numbers, plots. Can you even imagine going in and deleting every single one of those out of your working memory and history? That probably initially sounds scary, but if you start that way from the very beginning, every time you try and compile your paper, you wipe the slate, you annihilate everything, then you rebuild it, that gives you incredibly high confidence that you can do it. Because if you ever screw that up, you're going to realize it immediately. You're going to go back and fix your bug. So I know every time I run this script that I can build my entire paper, I can build my data sets, I can build my figures. I know I can do it because I am doing it. I'm forced to do it. These lines force me to have complete reliability in generating every part of my paper. So now we run the data set, and then we go to analysis. This is very similar to the code before, but you'll notice some differences. So I still have code here to figure out what percentage of cars get above 20 miles per gallon. But instead of just printing that to the screen, what I do here, this cat command, basically prints that number to a file, out number, and I give it a name, prop20 mpg.txt. And actually, to show you how this works, I'm going to run this command. So the idea is every time I make a change to my paper, I would destroy, I'm in the wrong folder here, see, good example, and build. I'm going to build this every time I make a change. And this thing should pass with flying colors and generate a paper. If we go down here, out paper, there it is. 44 cars, all that. We'll look more at that in a minute. But now take a look. In my out number folder, I have a text file that contains the number 44. Okay, interesting. Now, instead of having to remember that and go into my paper and hand paste that in and hand paste it into my slides, let's take a look at the paper. Here it is. In the empty cars data set, blank of the cars attained 20 miles per gallon. I am inputting that text file. So every time I compile this paper, it's reading that number from the file and putting it in here. One minor little thing I have, which there may be a better way to do this, when you use the normal LaTeX way to do this is just called input/input, but it leaves an extra space. Through some trial and error, I figured out if you add a command, you can name it whatever you want. I named it input Y for no particular reason. It gets rid of that extra space. So I use this little input Y. But now, let's say I find an errant data point and have to fix it. When I run build.sh, it will regenerate that number. Let's say it becomes 41%. Well, that will automatically get pulled in here. I don't have to go back and change anything. Let's look at slides. Same thing. I pull that number into my slides. And there you go. No further work is required. Now, again, imagine you have 300 tables and plots. You could go make one tiny little change to fix it, and it would regenerate everything perfectly accurately for your entire project, right? Let's go look at the rest. So we looked at prepared data sets. We run analysis. That was the number. Here's our stargazer. Instead of printing to the screen, we're saving it, this lm table variable. And then these lines, write lines, will save all that text to a file. I saved it here to the out table folder. So let's take a look at that. lm.mpg.txt. Boom, there it is. There is our LaTeX table generated by Stargazer. And you'll also notice I already started doing some formatting here. Title, predictors of miles per gallon, and empty cars data set. You can set the font size. Here I put it to tiny. And basically you want to, in code, make your table look exactly like it needs to look in the LaTeX document. If you have to do any further hand modification, it doesn't work. You break the process because now you still have manual steps. Anything that can be automated has to be automated. We do the same thing with Xtable. Xtable will generate our LaTeX table, but instead of copying it and pasting it, we print it into a variable here, table mpg by cylinders, then we write those lines and we get the exact same thing. We get cylinders and miles per gallon, we get another LaTeX table. The other thing you'll notice here that I did differently than the bad example is I actually set the column names here. I set the label, I set the caption, I hide row names, I set my LaTeX placement here, all in code, because this needs to come in exactly the way I want it to look in LaTeX. And now if I go back to my paper, here we go, input. Instead of pasting in copied Stargazer or Xtable code, I'm just inputting these tables. Same thing for the Xtable plot. And then the last one was the plot command. So we go back to our analysis. Here's our file. We are creating a PNG file in the out figures folder. And we're setting all the variables the way we want them. And then we do dev off, which saves it. And now if we look in our figure, there it is. There's our plot. And slides has all of this as well. Here's our two tables. And here's our plot. So every piece of our paper and our slide deck is automatically generated every single time we make a change, right? So we could just do something, very similar. Something very simple. We just have a typo that we need to fix. We'll save it. sh build.sh. We regenerate everything. And at the end of the day, actually go back to our build.sh, our last steps here after we run analysis, these lines create the paper and the slides in the appropriate output directory, and then we clean it. This just deletes all the extraneous files that LaTeX creates along the way. And we end up with the paper and our slides. So you can see the power of automation here. So just to prove this point, let's say that we were writing this whole paper not realizing there was a bad data point. So open our data. Let's say the Mazda RX-4, which has a miles per gallon of 21, was erroneously input as 2100. Someone had a units conversion error. All right. And we'll go ahead and run the paper, or run our script to generate everything. And go ahead and load the paper. Now that plot does not look right. We've got almost everything flat, low miles per gallon, and there's an outlier up here at 2000. So let's say that we were nearly done with our paper. We didn't notice it when we were running our regressions. We thought we had amazing results. And we get down here and see this plot and say, uh-oh, there's something wrong. We do some research, go back, look at our data, and then we spot it, right? Well, we could spend hours redoing our entire paper and hand checking everything, or we could just fix it and run a single line build. Take a look at our paper. There it is. We have a normal paper, normal regression. Our effect dropped from like -35 to -4. Our results not quite what we were hoping for, but hey, still significant, so we're good. So this shows you the magic of automating what can be automated. We've also got a very clean file system. Were we to give this replication data to someone in our code, they in theory could run that one line and get the same results we did, and they have everything they need to start tinkering and modifying and changing, and they can regenerate and trace through the effects of every change they make, which is reproducible science, at least the parts that are controlled here. This is not all sufficient. There's further things we would do. It's possible that a replicator's environment on their computer could be different than ours. We took one step towards dealing with that by installing packages if they're not on the system. There are other things we can do which are more advanced that we can actually kind of run this in a containerized environment that should in theory be the same on every system that runs it. That's a little bit beyond scope. Maybe we'll touch on at the end of course. But if you can do this, you are so much farther than most people. So I've focused a lot on automation in this overview video, but that's not all. This whole thing also lives in source control. This is probably where I should have started, but it takes some explanation, because putting your software in a version control system is the single most important and critical thing you have to do. Any good software developer would be horrified at the thought of running any kind of large project outside of version control. It happens, it's terrible, but most of us in grad school don't learn about version control. So we will dive into it later. It is a learning curve, but let me show you the power of it. So this whole thing lives in a system called Git, which is the most popular. It's the only one I'm going to talk about because it's so popular. It's the one I know. I would just recommend using it unless you have a reason not to. And the way you start with Git is you make a folder into what's called a repository, which is just a place where code lives. So I'm going to go into my shell here. to show you what a Git repository looks like. Here's a list of all the files, and you'll notice there is this .git folder. You can take any folder and run something called Git Init, and it will turn it into a Git repository. And if we go into that Git folder, there's a bunch of stuff that we don't need to concern ourselves with. This is all the black magic under the hood that's going to keep track of all the changes that we make. And what's going to happen is all of our code gets put in a version control system. I'm going to use a tool called Source Tree that interacts with Git so we can graphically look at what a repository looks like. My folder is called Research as Code. And basically the way Git works is you do some work in your repository, and then when you make a change, you generally think in terms of making small incremental changes. After some meaningful change, you do what's called a commit. You tell Git, hey, I made a change to readme.md. I want to save my change. And that's my initial commit. This was built by an online Git hosting tool called GitLab. And they created automatically this readme.md, which I don't really need, but they created a commit when they added that file. Now, when I took over it, I don't need most of their garbage, so I went in, and you'll notice over here, I can see the difference between the old version and the new version of a file. Here's all the stuff I got rid of in red, and I added my own line, sample projects to demonstrate how researchers can benefit from software management best practices. This was one cohesive change. It makes sense in my mind. This is one change, so I saved a commit. And this is the entirety of my repository. Everything you add in that folder, you tell Git as you go which files to track. And then from that point on, once you make a change, Git will keep track of the differences in those files. You can create a file called .git ignore, which tells Git, hey, you need to ignore the following things. We don't want to check them into version control. You can find default Git ignores for every programming language out there pretty much. So in here, I added the LaTeX one. And then I added another commit later for all the files for R. What kind of things don't you want to add? Well, remember how we destroyed every output item generated by our code? You don't want to commit those into version control because anybody who downloads your code should be running that script to generate all those things themselves. In fact, you really don't want old outputs because it's just clutter. You don't know where they came from. You can't trace them. You want to get rid of that stuff. So somewhere up here, I don't remember where I put it in my commit history, I actually add the whole output folder here saying don't add the output folder to Git. Then I go and I create my project skeleton. Here I've added there it is. I added the output folder to my Git Ignore. You can see I've Git Ignore highlighted and output here. I created a very simple build script. It just creates those folders. It generates the paper and slides. I created very skeletal documents here. There's no content in them really for the slides and the paper. I'm not even running any code yet. I haven't written any R code. I add my data set, data empty cars. Now this does raise a point we'll talk about later. Normally you would want to version control your data. In this case, this data file is only 2 kilobytes, so I can store it in my repository. And remember how we did that demo with the wrong data point we had to fix? That's the perfect kind of thing you want to track in a version control system because I can go back and look at my code at any point along here. I can check out this version and say, hey, here's what my code looked like when I had this version of the data set. And I could go run sh build.sh and it would generate an entire paper based on what was in that version of the data set at that time. Later, if we fixed something and committed, we could load up that commit and see the state of the paper based on that version of the data set. Your data and your code are always in sync. In practice, most of us work with big data sets that we don't want to put in Git. Git isn't really designed for large block data like that. There are other solutions for version control. It gets a little bit more complicated, but you get the idea. So the beauty here is by working in version control, I can look at this commit history and see the entire history of this project. I can see what you as a scholar were thinking, how you systematically built out your paper, your code. I can see where you fixed bugs. Maybe you introduced a bug. Maybe you're working in a team and someone on your team introduced a bug that you're trying to track down. You can go through the commit history and look at who was working on the code on what day and figure out where that code was introduced. I've got my R code introduced here. I can see where that was added. If we were fixing bugs and changing things, you would see a pattern of red and green. When you get really advanced working in teams, multiple people can work on the same code base at the same time by working in what are called branches. You could think of this blue line as a river of code from start to finish. It's always flowing, and different people can check out a version of the code, make a copy called a branch, and you would actually see a line branching off down here. They would work on their own version, and when they're ready, they would merge it back in. That's all advanced. We're not going to go there in this course. But now you've solved the problem of having version 1 through version 27. You've solved the problem of having unknown versions of artifacts like pictures and tables, unknown versions of your document, your code, your data, all floating around, because all we have in here is a source data set and the code to generate everything else. And we could easily pass this to anybody else. We can load our code at any point in previous time. You don't need to save all that commented out old code that you think you might need someday, because it's all in version control history. You just delete it, commit, and then if you ever need to go back, just like here, it's all in there in red. You can go pull it out again.